exponential and the logarithmic. The exponential and logarithmic functions. Tremendous real-life applications. We have to start with the exponential. We will talk about exponential, then we look at logarithmic functions, and then we'll look at properties of logs, and then exponential and logarithmic equations, and then word problems. That's the whole thing. So we start with 4.1, exponential. Functions. What do you think? Why do we call this function? By the way, how do we call it? How do we call this function? Right. Why do you think we call it the absolute value? Right. Why do we call this function square root, right? Why do we call it a square root? Right. So then why do you think we call this function exponential function? Right. And furthermore, the exponent is the variable. This is a constant. It's known. So a to the x, and in your book, I just wanted to make sure that they don't use b. In some books they use a, in some books they would use b. So this is a constant, and it's a known constant given to us. Now here's the question. Can I raise 0 to the third power? What do I get? Good. Can I raise 1 to the fourth power? 1 times 1 times 1 times 1. How much is that? 1. Can I raise -3 to the fourth power? Right? I get 81, correct? So this is 1 and this is 0. However, these are not possible for the exponential function. Not allowed. So the question is why? I can raise 0 to any power I want. I can raise 1 to any power I want. I can raise a negative number to any power I want. How come that this base cannot be, this is one case and this is the other. The base cannot be anything else but a number greater than 1 or a number between 0 and 1. So 0 is not allowed, 1 is not allowed, negative numbers are not allowed. They exist. We can work with them, but not when it comes to exponential function. Why? For only one reason. Logarithmic function, which you will see is the inverse function of the exponential, will not exist. This is the only reason. Not because 0, 1, and negative numbers cannot be raised to different powers. They can. But the logarithmic function, which is the inverse function of the exponential, will not exist. So log cannot have a base of 1, 0, or negative. So therefore, like we did with sine to make it 1 to 1, same thing here. For the exponential function, we have to restrict the base, not the exponent, not the variable, but the base, because the logarithmic function will not exist. That's the only reason. So there are two different shapes. So we have to look at f of x equals 2 to the x. We have to look at f of x, let's say 1/2 to the x. And we do have to look at the other two that are in the graphing calculator. Here they are. 10 to the x and e to the x. These are special functions. This is called common exponential function, and this one is called natural exponential function. And these are present in the graphic calculator. Although your new calculators allow you to change the base with whatever you want, not just these two. The old calculators, like the one that I have, which is an 86, and I'll show you the other calculator that we have, but 84 I think it is. As you see, here we have log, which is log, and in yellow, or the second key, is 10 to the x. And also we have natural log, ln, which with the yellow key, or the second key, is e to the x. So these are special keys for those functions. Log and natural log, and e to the x and 10 to the x. Okay? Good. So let's start by graphing and talking about 2 to the x, then 1/2 to the x, and these two will have the same shape with 2 to the x. So all these with a base greater than 1 will look very similar, will be very similar. This will be very different with a base less than 1. So we have one option greater than 1, and the other option is between 0 and 1. Not 0, not 1, and not negative. So let's look at f of x equals 2 to the x. Can anyone identify the domain for this function? And then we'll establish if it's a friendly function like polynomial functions or not. I saw in your tests that you graphed asymptotes for polynomial functions. I don't remember, and if I did remember, I would not say who it is. I don't remember. But I saw vertical asymptotes for polynomial functions. That's not possible, right? Polynomial functions are very simple, continuous functions, no asymptotes whatsoever, right? Rational functions have asymptotes, horizontal or slant or vertical, but not polynomial. So now we're going to establish whether the exponential function is a friendly function, in other words, defined everywhere, no problems whatsoever, or is not. So what do you think? What about -3? Can I raise 2 to -3? Yes. So this is 1/8. So this is a friendly function. Exponential function is defined everywhere. Very friendly. No headaches whatsoever. I can plug in anything I want in that function. So I'm going to choose -2, -1, 0, 1, 2. I did not scientifically choose these numbers. I just want to see what happens around 0, not too far away from 0. So let's plug in -2 in the function, like f of -2 equals 2 to -2. What will that equal to? Very good. Okay, 1/4. So now please plug in -1 and tell me what you get. Okay, f of -1 is 2 raised to -1, which is good. So please plug in 0 and tell me what you get. Very good. Please plug in 1 and plug in 2. Good. Now, again, this is not a scientific way, but this is how we determine the end behavior for this function. Let's try. Let's see. Look at the pattern. 1/4, 1/2, 1, 2, 4, 8, 16, 32, 64, 128. Where am I going? Excellent. Let's go this way. 4, 2, 1, 1/2, 1/4, 1/8, yes, very good. What does this mean? We learned this in the previous chapter, in chapter 3. When x approaches -infinity and y approaches 0, what does that mean? As x decreases without bound, y approaches a number. What does that mean? Very good. Y equals 0, a horizontal asymptote. Excellent. But I'll have to say, only at negative infinity. As you see, there is no number here. It's infinity. So now let's graph this function. Please give me the first ordered pair that I should plot. Negative 2, comma. I didn't take my own advice. I know it's an overkill, but I have to graph the asymptotes first when I graph a function with asymptotes. So negative 2, comma 1/4. What is the next ordered pair I need to plot? Negative 1, 1/2. Good. The next ordered pair. Good. Next ordered pair. And the next ordered pair. So please pay attention to the graph. Here it is. It does not touch the x-axis. So this is the function f of x equals 2 raised to the x. Now, can you tell me any properties of this function? Can you list properties of this? For example, what is its domain? So I'm going to say this function is defined on domain. What is its range? Very good. I don't know anything about this function, but will it be 1-to-1? Is this function 1-to-1? By the horizontal line test. For each y, there is only one x. So it's 1-to-1. It will have an inverse function. Can anyone identify, although we don't know anything about the inverse function just yet, can anyone identify its domain? That's what the inverse function does, right? So 0 to infinity, and this is not a friendly function. This is a friendly function. Look at its domain. This is not friendly. What do I mean by not friendly? It's a function with restrictions. So the inverse function would not be defined everywhere. It will only be defined on positive values, not even 0. So this is a function with problems, like the rational function. It's not defined everywhere. Like the square root. It's not defined everywhere. This is the third one this semester. It's not defined everywhere. It's defined only on positive numbers. So we will have a problem. Now, can you give me a few ordered pairs so I can graph it? We still don't know what it is, but I would like to be able to graph it. I would like to graph it here on the same Cartesian system. Very good. 1/4 negative 2. Very good. Very good. And this is the inverse function. And they must be symmetric with respect to the line always the function and its inverse are symmetric with respect to the line. We are reversing them. Which line? Exactly. Absolutely. Y equals x. So in other words, I'm saying these two have to be equidistant, at the same distance from this line. These two have to be at the same distance. Of course, they are not perfect. Sorry. And so on and so forth. Same distance from y equals x. Same distance from y equals x. Very good. So what else we notice here? That this function has a horizontal asymptote. Its inverse will have a vertical asymptote. X equals 0. They are both 1 to 1. They are both increasing on their domain. So when the function, the exponential and the inverse, have a base greater than 1, they are both increasing on all their domain. Okay? So now let's look at the other shape. What other shape? The exponential function with a base less than 1, like 1/2 to the x. What is its domain? Like the domain of any exponential function. Yes, no restrictions. Not scientific, but I'm going to pick the same numbers. Please plug in -2, like f of -2 is 1/2 raised to -2. How much will that be? You have to flip a fraction and raise it to that power. Very good. Now f of -1, 2, f of 0, f of 1, f of 2. Very good. Again, not a scientific way, but this is what we do with the exponential function, with the end behavior of the exponential function. Can anyone tell us where are we going this way? To the left. 2, 4, 8, 16, 32. Infinity. And where are we going this way?
0.
Yes, indeed. Very good. What does that mean? When x approaches infinity and the function values go closer and closer to a number, what will that mean? Y equals 0, horizontal asymptote at infinity only. So now let's graph this function. Can anyone give us or give me the first ordered pair I should plot? So -2, 4. Next ordered pair. Very good. Next one. And of course, I forgot again, y equals 0 is a horizontal asymptote. Good. Next one. And 1/4, and it becomes more and more difficult to plot. So this is the graph of 1/2 to the x. What is different from the previous shape? And actually, that's the only thing that is different. So here is the previous function, 2 to the x, and here is 1/2 to the x. What is the? It's only decreasing it. Everything else is the same. It's 1 to 1. The domain is the same. The range is the same. It's just that it's decreasing, and it has an inverse function. Can anyone give us some ordered pairs to graph the inverse function? And we will graph it symmetric with respect to which line? Good. Which means wherever this function crosses y equals x, the other one has to cross at the same point. Because this point is, let's say, it's not. But let's say it's 1, 1. When I reverse it, it's still 1, 1. So please give me a couple of ordered pairs so I can graph the inverse function. Very good. 4, -2. 2, -1. Yes. That's enough because I already have another point on the other side. So this is f inverse. As you see, a function with problems. Why? It's defined on 0 to infinity. It's not a friendly function. Now, if I say to you, let's graph this function, f of x equals -2 to x plus 2 minus 4, plus 4, let's say. And I'm going to ask you to use transformations to graph this function. What will you say? What is the base function? The function that was used to build this function, of course. What is the first transformation on 2 to the x in order of operations? Yes, 2 to x plus 2, left 2. In order of operations, the next transformation on number 1. This is a reflection. So 2 to x plus 2 reflect with respect to the x-axis. Everything that is positive becomes negative now. And finally, the third step is up 4. Very good. Now, before we present the transformations, I'd like to do 2 things. I'd like to find 2 things. I would like to find the x-intercept, because this is a one-to-one function. You cannot cross more than once. So how do I find the x-intercept for any function? Yes, I said y equal to 0, so -2 raised to x plus 2 plus 4 equals 0. Okay, how do I solve this equation for x? What will you tell me to do first? You will say you have to absolutely clean it up. Exactly. Good. Then you will tell me to
find x plus 2 root of both sides.
in a second, not yet. I haven't cleaned it up completely. Yes, multiply or divide by -1. Now, I see that the left-hand side has a base of 2. I'm thinking and hoping that I can present the right-hand side with the same base. But can I? Yes. So then the left-hand side is 2 to x plus 2. The right-hand side will be rewritten as? Very good. So here's what I'm telling you now. I am not eliminating the base. I am not dividing by the base. I am not simplifying the base. I'm not erasing the base. Here's how we think. 2 numbers are equal, and they have the same base. What has to happen to their exponents? One more time. 2 numbers are equal, and they have the same base. What has to happen to these exponents? They have to equal each other. So from here, I know that x plus 2 must equal 2, which makes x be 0. So then the ordered pair that represents the x-intercept is comma 0. 0 for x, 0 for y, because that's how we started. Okay? Is there a point in trying to find the y-intercept? Remember, this is a one-to-one function. If it passes through the origin, it cannot pass any cross x-axis or the y-axis anywhere else. Good. So now this is something that I wanted to determine. This is our first exponential equation. We just solved our first, the easiest possible exponential equation. This is it. 2 numbers are equal and they have the same base. This rarely happens. In other words, I'm saying very rarely the base here equals the base here. So this is really a treat. Okay, so now I would like to graph these. So first I have to graph the base. Here's the base. 2 to the x, it crosses at 0, 1. So this is 2 to the x. Now you told me to shift it left 2. So this point from 0, 1 will go to the graph, the whole thing, not just one. But if I want to shift this point 2 units to the left, where will it go? Right, exactly, at -2, 1. So then this is the graph. This is the graph of 2 to x plus 2. Now, you told me to reflect with respect to the x-axis. Okay, I'm reflecting with respect to the x-axis. Where will this point go? Very good. -2, -1, correct? Very good. So here is the graph now. So this is the graph of -2 to the x plus 2. Notice that all these three graphs have something in common. What do they have in common? A horizontal asymptote, y equals 0 at -infinity. Then at the end you told me to move this graph up 4 units. What do I have to move first? Before I move the graph, this graph has to be moved up 4. What? Yes, 1, 2, 3, 4. So this is y equals 4. This is the asymptote of the function I need to graph, which is the final function. So where does this point go, which was now at -2, -1? Where will it go? Right here. And what did we find out before we even started using transformations? What did we find out about the function? That it crosses at the origin. So here's the graph. So this is the final graph, which is for f of x, -2 to x plus 2 and plus 4. I'm looking to use this in our first word problem. Um, 53 caught my eye. The formula will be given to you. So here is, before we do that, I think I'm on page 6, yes. Before we do that, I would like to just mention f of x equals 10 to the x and f of x e to the x. I'd like us to look at those graphs, very similar to 2 to the x. So let's do this with a graphing calculator. So you can put both functions in y equals, clear everything else. So just 10 to the x and the second one, I didn't mean that. What is it doing? X. Okay, and e to the x. So in the software, with the software, you'll see one will be in blue and the other one in red. Which of these two, before we click enter, and of course I have to check the viewing window, and I'm going to use standard, but which of these two you think, obviously they will have to look like this because the base is greater than 1, right? Correct? Which of these two will be further away from the y-axis and which of these two will be closer? Remember, E is 2.71, 10 is 10. So raise both of them to power 2. 2.71 to power 2 and 10 to power 2. Which one will be closer? 10 will be closer because the number is higher, right? 10 squared is 100 and 2.7 squared is less, much less, right? So the first function will be closer to the y-axis than the second one. So now let's go to zoom and 6. Here's 2 to the x, and here's e to the x. Further away, because the base is smaller. Okay? We know they don't go on the x-axis, they don't touch the x-axis till who knows when, down the road. So that's the error of the calculator. As you see, they both cross at 0, 1 because 10 raised to 0 is 1 and e raised to 0 is still 1. Now, if I want to graph the inverse function of the blue function, which we will do by hand in a few minutes, please punch in log, L-O-G-X. That is the inverse function of 10 to the x. I'm going to, for a moment, de-highlight this one. I only want the function in its inverse. So now please press graph. Again, we know the calculator is lying. This function cannot start here negative infinity or negative 10, and this one starts at negative 1 for y. It's impossible. These two functions are inverses of each other. So please make a note. Look how the calculator shows this, starting here, and it does not show that this one should be a mirror image with respect to y equals x. So if I put in as the next function y equals x, doesn't matter which one it is, here it is, right? So this has to be completely symmetric of this, 100% symmetric of this with respect to this line, but that's not the case. So please do not trust the calculator entirely, fully to do the work for you. So now in y equals, if I want now to de-highlight this, and I want e to the x, and I also de-highlight that, and I would want the inverse function, which is ln. It comes from German. It should be for us NL, natural log, but is ln because that's how they consider it. In German, it's also I'm sorry. I have to highlight the e to the x. That's what I wanted to. Okay. So now let's see these two functions. Again, the calculator is lying, and we know it's lying. So that's e to the x. That's the inverse function, not possible. It cannot start there at -2. That's an error. So if the calculator shows this, it should show this because these functions are inverses. Both cases base greater than 1, both increasing. Okay, enough of that. Any questions? So both 10 to the x and e to the x look very similar to 2 to the x, okay, with a base greater than 1. And now I would like to look at compound interest. So here are the formulas. There are two formulas that we will look at. I will give them to you. So A equals P e to RT. What does this mean? A is the accumulated value. P is the principal. E is a number, Euler's number, 2.71. R is the annual interest rate, and T is time in years. And this is for continuously compound interest. If the bank you are depositing $1,000 to, if they continuously compound your interest, this is the formula they're using. If you are borrowing money from a bank, then P is the amount of money you borrow, and A is the accumulated value down the road, 20 years, 30 years from now, in case they are continuously compounding interest. R is the annual interest rate, and T is the time in years. Now, there is a totally different formula, which I will give you. You don't have to memorize it, which is this. A and P have the same significance, R the same significance, T the same significance. But N signifies not continuously compound interest, but interest compounded N times per year. N is the number of times the interest is compounded per year, which can be once a year, twice a year, 12 times a year each month, 52 times a year each week, 4 times a year each quarter, 3 times a year, and so on and so forth. So, in problem 53, compound interest. If 500 is invested at an interest rate of 3.75 per year, 0.0375, it has to be changed into decimals. Compounded quarterly. What does that mean? N is how many quarters are in a year? 4. Find the value of the investment after the given number of years. So for T equals 1, for T equals 2, for T equals 10. I would like to determine the continuously compound interest. So let's do this. In Y equals, clear everything, we don't need this anymore. And put in the formula, which is, I should have, let me write it first. So the formula is A equals 500 in parentheses 1 plus 0.0375 divided by N, because I'm going to use X instead of that, and multiplied by, we're given 4, I'm sorry. Multiplied by 4 times T, which will be X in our problem. So let's put in the function, put in X for T, and then do a table. So 500 in parentheses 1 plus 0.0375, let's say 4 times a year, caret, in parentheses, I have 4x. I don't have T in the calculator, so I put 4x. And now, with second and table, I will punch in 1, 2, and 10. 1, enter, 2, enter, 10, enter. And just go back up. So A for 1 year is $519.02. A for 2 years is 538.75. And A for 10 years is 726.23. Now, if I want to determine what will happen for the continuous compound interest, Tony, you wanted to see it again?
No, I don't.
If you want the continuous compound interest, I don't need a table because it's just one formula. It will be 500 times E no, not 10, times e raised to, in parentheses, n r times t, r which is 0.0375, 0.0375 multiplied by 1 year. Oh yeah, I really wanted that as a function though. Okay, never mind. Multiplied by 1, multiplied by 2. So I'm changing 1 into 2. And change it now to 10 years. So 10 and close. So if the interest were compounded continuously, A of 1 will be 500 times e to 0.0375 times 1. And we got 519.11. A of 2 with the same formula, 538.94. And A of 10 with a continuous compound interest, 727.50. That's how we use those two formulas. On page 313, I'd like to look at problem 22. Radioactive decay. I mentioned that exponential and logarithmic functions have tremendous applications. So here is a little list, a short list of applications of exponential and log. Number 1. When a person dies, the date, not the date, but the time and the date, I should say, of the death can be determined with a function that has log in it. When you take a turkey out of your oven, when you cook the Thanksgiving dinner, the temperature of the turkey decreases using the log function. When you get a loan for a car or a mortgage for a house, the monthly rate is calculated using an exponential function. Every time I get a loan of any sort, I have programmed in, I have a lot of different applications here, but I have one application that is called annuity. Here's the annuity formula. So before the clerk at the bank even tells me anything about anything, I tell them already how much I have to pay per month when I take a loan. So I have this annuity formula. For example, let's say we want to borrow $200,000 for how many? For 30 years, let's say, and the rates are still low, 0.03, let's say, right? When I press enter, it will tell me exactly how much I have to pay, only interest and principal. It doesn't say anything about insurance for the house. It doesn't say it's not included. Property taxes are not included. But I tell them right away that I have to pay $843.21 per month. So in this formula, in this program that I created here, it's nothing else but an exponential function. They don't know how this is calculated. They are just punching something in the calculator and it gives them a spreadsheet with how much you have to pay per month. But they have no idea what formula is in there because they already have the software. Okay. So radioactive substances decrease their mass using an exponential function. Bacteria grow exponentially. So a model or a function that grows the Zika virus or the Ebola in Africa is using an exponential function. Birds grow normally exponentially. Populations in general grow exponentially unless, like the Germans, have a big problem. That's why they invited more than 1 million Syrians in there, because their population is fading out actually. Rat population grows exponentially. Birds, I think I mentioned, grow exponentially. Tremendous applications using exponential functions and log functions. Okay, so radioactive decay. Doctors use radioactive iodine as a tracer in diagnosing certain thyroid gland disorders. This type of iodine decays in such a way that the mass remaining after T days is given by the function. We have the function. So M of T, mass function of time, equals 6 times e to negative 0.087 t, where M of T is measured in grams. So this is in grams. Find the mass at time t equals 0. So part A, I'm asked to find what happens at t equals 0. What was the initial amount? How do I determine the initial amount? Bless you. By plugging in 0. So M of 0 is how many grams? So how much is 0 times this number?
0.
How much is e raised to 0?
0.
Careful.
1.
1. Any number raised to 0 is 1 except when the number is 0. So e is 2.71, raised to 0 is 1. How much is 1 times 6? 6 grams. In part B, how much of the mass remains after 20 days? So 0 days. So t equals 20 days. I cannot do this by hand. I have to punch it in the calculator. So here's what I'm going to write or type. 6e, in parentheses, you know me, maybe your calculator doesn't need parentheses, but I'm petrified of lack of parentheses. So I multiply by 20 and close the parenthesis and press enter. So in 20 days, it will decrease from 1 gram to, from 6 grams to 1 gram, 1.053. So M of 20 is 1.0531 grams. I would like to look at problem 26 on page 314. Any questions? I think you're going to find, especially after we discuss exponential and logarithmic equations, I think you're going to find this chapter friendly. Okay. Look at the bird population. So here's a function. A bird population. The population of a certain species of bird is limited to the type of habitat required for nesting. The population behaves according to the logistic growth model. Here it is. It's given to us. Very complicated function. Very difficult to come up with. A lot of research was involved in creating this function, where t is measured in years. Find the initial bird population, draw a graph of the function, we'll do it with a graphing calculator. What size does the population approach as time goes on? So, when you copy the function, so it's n of t, n signifies number, m here signifies mass, so n of t equals 5,600 divided by 0.5 plus 27.5 times e to negative 0.044 t. Okay, t is measured in years. Okay, first question, find the initial bird population. What am I asked to do? When I'm asked to find the initial bird population. Exactly, n of 0. So let's see what we have. When t is 0, what happens to this quantity? How much is e to 0? How much is 1 times 27.5? How much is 27.5 plus 0.5? 28. How much is 56 divided by 28? 200, yes. 200 birds. Good. Part B, draw a graph. Okay, so let's take a look. Let's draw a graph. Before that, I want to ask a question. I would like to look at part C before we graph. Part C. Now, we're asked to find what size does the population approach as time goes on. Okay. What does, when we say time goes on, what do we really mean? Exactly. That's what we mean. Of course, we cannot say infinity, but we mean a lot. So let's decompose the denominator. I'm talking about the denominator right now. When t approaches infinity, how much does negative 0.044 times t approach? So I have 10 billion, and I multiply by negative 0.044. What will I have? 100 billion. 200,000 billion. Multiply by this. Where will this go? But when I multiply 10,000 by negative, it doesn't go to 0, right? It goes to negative infinity. Perfect. So when t approaches infinity, some negative number times t will approach negative infinity. I don't care how small this is. This is infinity times whatever. It's negative. It goes to negative infinity. Okay, now I'm discussing e to negative infinity, which is 1 over e to infinity. So e to infinity is roughly 3 to infinity. Where does this go? 3 to infinity, where does that go? Perfect. Where does 1 over infinity go? We had that in type 2 of rational functions. 1 divided by infinity, where does it go? Excellent. So now I have that when t approaches infinity, this approaches negative infinity, and this approaches one more time? 0, right? You just said that, correct? Okay. So how much is 0 times 27.5? 0. How much is 0 plus 0.5? So then how much is 5,600 multiplied by 2? Because this is 1/2, and you have to multiply by 2. So that's 11 to 200, right? So what I'm telling you is this. As t approaches infinity, where do the value of the function go? Closer and closer to 11,200. One more time. Let's do this one more time. As t approaches infinity, this approaches negative infinity. E to negative infinity approaches 0. 0 times this is 0. 0 plus 0.5 is 0.5. But 0.5 is 1/2. So I got this multiplying it. So as t approaches infinity, n of t approaches 11,200. What does that mean? So as t approaches infinity, n of t approaches 11,200 birds. But what does that mean for this function? As x approaches infinity, the function values approach a number. What does that mean from the previous chapter? Horizontal asymptote. Y equals 11,200 is a horizontal asymptote. Now let's graph. In y equals, clear everything, and let's put one function is 5600. Okay, it's one number at the top. I'm going to omit parentheses for the top. Okay, 0.5 plus 27.5 times E. Careful with parentheses now. Negative 0.044x. Close the parenthesis for the power. Go outside and close the parenthesis for the denominator. What will be the second function I need to graph? Thank you. Now the viewing window, I cannot use the standard viewing window. So the viewing window will be for x between 0 and 10, that's fine. With a scale of 1, that's fine. Y minimum, it cannot be negative, so 0. And how big should y be? If the horizontal asymptote is 11,200, I went to 11,500 with a scale of 2,000. And let's press graph. Here comes the horizontal asymptote. I have to change the view drastically, the viewing window. So let's go to 500 with a scale of 50. Ah. Here it is. It levels off, and here comes the horizontal asymptote right now. So I used 500 here, so 50, 100, 200. So about 200 years, that's T is in years, about 200 years, if the model still holds, they cannot grow more than that. It's going to be very difficult for them to live in that particular habitat because there is a cap, and the cap is 11,200. So 200 years, fine. Another maybe 50 years, fine. But beyond that, there will not be enough room in that particular habitat, assuming the model is still true at that time. Any questions? Okay, so now let's talk about the log function. I lost track of, so this was 7. So these were examples in which we used the exponential function. So now this is 4.3 log function. Before, we already graphed the log function. We're going to graph it again, of course. But we already know how it looks like. I know one option is this, with a base greater than 1. And I know the other option is this, with a base less than 1. I graphed the, the log function already. However, before I get there, and we're going to plot points and everything, we're going to do it from scratch, I need to present the most important concept in this chapter. The most important concept in this chapter is this. First, in plain English. Any logarithmic equation can be written or transformed or as or into an exponential equation. Comma, and vice versa. This is the most important concept in this chapter. Any log equation can be written or transformed, written as or transformed into an exponential equation, and vice versa. So this is in English. How do we write this in mathematical terms? And here it is. And here's the notation for the log. We already seen two of them. We saw log and we saw ln a few minutes ago. So log base a of x is y. So I'm going to write this in words. Log base a of x is y, or equals y. This is equivalent to, this symbol is double equivalency. Double equivalency symbol. Which means the left will imply the right will imply the left. So now please pay attention to this transformation from a log equation into an exponential equation. Here it is. The base raised to y is x. So counterclockwise, starting with the base. A raised to y is x. We cannot really do much in this chapter or understand much in this chapter without understanding or being able to change a log equation to an exponential one and an exponential into a log. And before we get to graph, again, the log function, I would like to practice this. On page 322, just changing a log into a log equation to an exponential and changing an exponential to a log. I want to practice this and then we'll come back to the graphs. Okay, here it is. Express the equation in exponential form. Express the equation in logarithmic form. So I would like to pick from here and I like to pick from here. I'm going to pick 10b. If you have any preference. 10b on page 322. Log base 8 of 4 equals 2/3. Can anyone give us the equivalency of this log equation into an exponential equation? We always start with the base and go counterclockwise. So, and I guarantee you that this is true. So this is the cube root of 64, which is 4. Now the other way around looks or is or may appear to be more difficult. So if I look at 15b, I'm going to write the equation, the exponential equation on this side. Of course, you don't have to use my method. But I prefer going backwards, seeing or watching the exponential or having the exponential equation on the right-hand side. I know I have to write a log. I know must be a base. There must be applied to some number, and there must be a number here. But now it's not difficult to change it, because I know what the base should be. What is the base? What power do I raise the base to? And what number do I get? 1/8. So that's how we go from a log equation to an exponential one, and that's how we go from an exponential equation back to a log. Let me know if we need more examples. If not, we'll go to graph the log function. Do we need other examples from 7 through 12? Yeah, what if we just do 18b? E raised to 0.5x, I think it is, equals t. Is it t? Yes, t. Very good. What did we say E is the same, or uses the same key with? Right. So ln. When we write ln x, let's say, ln applied, natural log applied to x, this really means this. But we don't use this notation. There's nothing wrong with it. By convention, we use ln x. So if you see ln, you know the base is e. You don't have to write it. So once I have here natural log, I know the base is e. So this must be applied to a number and it will give us an answer. So the base is already there, e. What do I raise e to? Yes, so this is 0.5x. And what do I get? T. Now, the other function that is, so this is natural log. Natural log. The other function that is in the graphing calculator is this. I don't see a base. Well, with no base, we really mean log base 10 of x. It's called common log. However, we do not use this notation, although in some books you will see it though, as the old notation. So 14a, we have 10 to the third equals 1,000. So I'm changing the exponential equation that I have on the right-hand side into a logarithmic equation on the left-hand side. So what do I write? Exactly. No, just log. So this is 10 raised to which power? So 10 raised to which power? Very good. Will give us what? Yes. Common log. Okay, so let's graph the log again from scratch. So let's say f of x equals log base 2 of x. One more time, log base 2 of x. That's how we read it. F of x equals log base 2 of x. And then the other shape, f of x, log base 1/2 of x. Which of these two functions will be increasing on its domain? The one with base 2 or the one with base 1/2? This was the graph for base 2. This was the graph for base 1/2. So which of these two graphs will be increasing and which will be decreasing? Yes, log base 2, any base greater than 1 will be increasing, and any base less than 1 will be decreasing. Perfect. So let's start with this. So f of x equals log base 2 of x. Okay, now the domain of this function. What is the domain of this function? Remember, it's not a friendly function. It's the range of the exponential. What was the range of the exponential? Go back to your notes, or I can go back to mine. So no. Yes, the range is 0 to infinity, and that's why the domain here is 0 to infinity. That's why it's not a friendly function. So the domain of the log is 0 to infinity. I will pick numbers that are base of 2, like 1 over 4, 1 over 2, 1, 2, 4. Okay? So first I need to determine log base 2, whoops, of 1/4. Well, I know that this is a number, but I would like to change this into an exponential equation so I can determine this number. 2 to some number equals 2 raised to some number equals, right, so 2 raised to a number equals 1/4. What is that number? Excellent. Log base 2 of 1/2 equals some number. This is equivalent to 2 raised to some number equals 1/2. What will that be? Good. Log base 2 of 1 equals some number. 0. Log base 2 of 2. 2 raised to some number is 2. Finally, 2 raised to some number is 4. Good. I'm going this way. I'm going this way, not in a scientific way though. -2, -1, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Where am I going? Good. The other way. Thank you. And it makes sense because the exponential function is defined everywhere and takes values in 0 to infinity. Now the log has to bring everything back. It's defined on 0 to infinity and brings it back to all real numbers. Perfect. So let's graph. I know I'm not going to graph anything here. First ordered pair, please. Got it. Next ordered pair. Next ordered pair. Next one. Perfect. And 4, 2. 1, 2, 3, 4, right here. So this is f of x log base 2 of x. Is this function 1-to-1? Does it have an inverse? What is its inverse? Very good. This is the graph of the inverse. Indeed, 2 to the x. Perfect. Now f of x equals log base 1/2 of x. The domain of log function. The domain is very good, not a friendly function. Again, I'm going to use powers of 1/2. So 1/4, 1/2, 1, 2, 4, 8. I apply log base 1/2 to 1/4. Log base 1/2 to 1/4 is a number, and this is equivalent to 1/2 to some number equals 1/4. 1/2 raised to some number equals 1/4. What would that be? 2. Very good. Now 1/2 log base 1/2 of 1/2 is some number, and this is equivalent to 1/2 raised to some number equals 1/2. 1. log base 1/2 of 1. 1/2 raised to some number is 1.
0.
Perfect. Log base 1/2 of 2. 1/2 raised to some number is 2.
Negative 1.
Negative 1. 1/2 raised to some number is 4.
Negative 2.
1/2 raised to some number is 8.
Negative 3.
Good. Which direction am I going here? Which direction I'm going? This way. Good. As expected, it has to return what the exponential function took. Again, I cannot graph anything here. First ordered pair, please. Of course, I want to mention here that x equals 0 is a VA. On the previous graph, please add it in. And also here, x equals 0 is a VA because it goes to infinity. So 1/4 2. 1/4 2. 1/2 1. 1 comma 0. 2 comma negative 1. 4 comma negative 2. And so on and so forth. And this is, can anyone tell us what this function is? F of x equals? What function did we graph? Log base 1/2 x. Is it 1 to 1? Does it have an inverse function? Can anyone give us the inverse function of this function? Very good. Here's the graph. Notice that it has to pass through this point and it has to pass through this point. So this is indeed 1/2 to the x. I have a few more minutes left. I just want to talk about problems 63 through 68. Page 323. Bless you. Okay, I'll choose the first one. 64. At 64, we are given log base 5 of 8 minus 2x, and this is a function f of x. We're asked to find its domain. Let me reconnect to something we did in the past. If I ask you to find the domain of this function, what would you tell me to write? Solve to get the domain. Dictate and I'll write it. Please. What do I have to write? What can this quantity be under a square root? Can it be anything? I'm sorry? It has to be greater than or equal to 0. Otherwise, I cannot take the square root. Good. So the same thing here. Here I had the equal symbol, but here I cannot have the equal symbol. So 8 minus 2x has to be strictly greater than 0. So negative 2x greater than negative 8. I divide both sides by negative 2. So the domain of this function is negative infinity to 4. Now on 66, I would like you to think for a moment and tell me what to write. The question is the same. Find the domain. What will you tell me to write?
So use x minus x squared is greater than 0.
Excellent. Now, what type of inequality is this and how do I solve it?
Quadratic.
Perfect. It's quadratic. So I will arrange it in descending order. I will definitely multiply both sides by -1. I refuse to solve anything that has a negative leading coefficient. And now I will factor. Now this is chart ready if you want to use the chart. So I have a product and I have 0. So if you want to use the chart, you will write this. You will study the sign of the first factor, you will study the sign of the second factor, and then you will study the sign of the product. So this is -infinity to infinity. What numbers will you put in the chart? If you want to use the chart, you don't have to. What numbers will you put in the chart, assuming you want to use it? Perfect. So it's 0 here, it's 0 here. Both are linear functions with a positive slope. They come from negative and go positive. 0 and 0 for the product. On the first subinterval, 2 negatives. What is the sign? Yes. In the middle subinterval, 1 negative. And the last one, no negatives. So I want this, because in the process it got changed. That's fine. But this is what I'm solving now. So the domain of this function is, it cannot be 0 because there is, so it has to be parentheses. That's it. That's the domain of this function, just 0 to 1. If you want to graph it, you can. Let's do that. I'm not going to ask you to do this, but I would like you to see it in y equals, clear, clear, bless you, ln in parentheses x minus x squared, close. And look what happens, assuming you use the standard viewing window, which you know it's not okay. Bless you. See the domain? Where was it? 0 to 1. So if you want, you can change the viewing window, please. Okay. 0 to 1. Those are both vertical asymptotes. 0 and 1. And -2 to, no, -5 to 5 if you want. And let's graph. Here it is. And this is 0, and this is 1. And these should have been vertical asymptotes. That's the graph between 0 and 1. Okay, any questions? Okay. Last problem, and I'll stop. Page 324. I can let you choose if you want. You want to use to look at the bacteria colony, investment, charging a battery. Look, charging a battery, it's a logarithmic function. Investment, logarithmic function. Bacteria colony, logarithmic function. Carbon dating, right here. Absorption of light, a log function. Just everything. Everywhere you go, everywhere you look. Difficulty of a task, a log function. So I would like to just illustrate with any of these. You choose.
90.
Which one?
90.
90. The charging a battery. Very good. Okay, perfect. The rate at which a battery charges is slower. It's slower the closer the battery is slower. The closer the battery is to its maximum charge, C0. The time in hours required to charge a fully discharged battery to a charge C is given by. I have to copy the function. So we chose 90 on page 324. Okay, so this is T equals negative K natural log 1 minus C over C0. C is again fully charged, and C0 is, no, maximum is C0, and C is the charge. Where K is a positive constant that depends on the battery. For a certain battery, we are given K, 0.25. If this battery is fully discharged, how long will it take to charge to 90% of its maximum charge? So what if C is 90% of C0? When I say 90% of C0, what operation do I mean? What does of mean? Very good. So C equals 0.9 times C0. So T equals 0.25 with minus in front. Natural log 1 minus C is 0.9 C0 over C0. What do you think we have to do next? When you look at this, you'll say, oh, I should,
Cancel out the zeros.
exactly, they are not zero, so what I have to punch in the calculator is this. How much is 1 minus 0.9? Good. So let's go to the graphing calculator, clear that, and I have negative 0.25, here's natural log, and 0.1. Careful, before we punch it in, do you think that natural log 0.1, here's the graph. Let me graph natural log one more time. Here is natural log, and it crosses at 1. Do you think that natural log 0.1 will be negative or positive? Natural log of 0.1, will it be negative or positive? So 0.1 is here. Where is the function? Where 0.1 is here. Is the function here or is the function here? If it's here, it's positive. But if it's here, it's negative, right? So at 1 is 0. At 2 will be positive. Anywhere between 0 and 1 will be negative, right? Okay, so now let's press enter. So I get 0.5756 hours, because T was in hours. So T, a little bit more than half an hour. So 0.5756 hours. I didn't write, but I think T was in hours, wasn't it? Just making sure. 324. The battery is fully charged. Okay, charged battery is lower. T in hours, yes. So a fully discharged battery to get to 90% of its capacity takes about this particular type of battery with a constant of 0.25, K equals 0.25, requires 0.57, roughly 0.6 of an hour. We finished the first 3 sections of this chapter, and on Wednesday I will continue. We'll continue with the properties of log. Log has 3 very special properties that no other function has, and then we'll look at exponential and logarithmic equations, and then word problems. Very good. Thank you so much for coming. If you have any questions, please stay. If I made a mistake in your grade, I apologize and I'd like to correct it.